Hello. I hope by now you have watched the course introduction movie and you are familiar with the various components of the course. You know how to access the various course materials and prepare and do well in the course. Well, if you haven't done so, please go and watch the course introduction before you start the course. Now, we will begin this course with a brief description on measurement. Well, once again, welcome to General Physics 1. What does measurement deal with? And what is the significance of measurement in physics? Well, of course, physics is full of measurement. Without measurement, there is no physics. We come across physical quantities all around us. And physical quantities are quantities that we describe by measuring. And in order to measure physical quantities, we need to use a unit. So we will first of all start with a description of units and measurement. All right. When you hear somebody says $5, you know that the quantity measured is money. When somebody says 5 meters, you know that the quantity measured is length. So what does unit of a physical quantity means? A physical quantity is identified by the unit of measure. Once you know the unit, you know the quantity that is measured. Now, we will use the SI system of measurement in this course. What does SI system means? It is the System International. That is the system used all over the world. Unfortunately, America hasn't come in line with the rest of the world about measurement. We still use the old British units. We still measure length in inches, feet, and miles. We still measure mass in pounds and all that kind of units which the rest of the world don't know. Now, we cannot do that in physics. We've got to follow the rest of the world. So we are going to forget about inches, miles, Fahrenheit, and so on, and we will be using SI units. All right. The unit of length in the SI system is a meter. Now, if you watch here, this is a meter stick. Well, it's too big to fit in the screen, is that right? I'm sure most of you have seen a meter stick. The unit of length is a meter, and we will abbreviate it by the small letter m. The unit of mass is a kilogram. Now, do you know how much a kilogram is? Well, I hope I could give it in your hand and make you feel. Well, give me a second. Here I'm holding a standard 1 kilogram mass in my hand. Well, it is a brass cylinder and its mass is 1 kilogram. Well, this is the unit of mass. And how do you represent that? Kilogram is kg, both lowercase. And the unit of time is the second. So the SI system of unit, length is measured in meter, mass is measured in kilogram, and time is measured in second. So very often it is called the MKS system. MKS system. Now, units of length, mass, and time are called the fundamental units of measure. Why are they called the fundamental units of measure? Because almost everything else can be expressed in terms of the units of length, mass, and time. The The units of all other physical quantities can be obtained by suitably combining these fundamental units. Now, meter is the unit of length. We talked about it. Now, if you look at this meter, this is the meter stick. Now, can you use this to measure the width of a hair? Well, I got to look for my hair. I got a few out here. If I take one of my hairs and I want to measure the diameter of my hair, can I use a meter stick to do that? Well, obviously, we need to divide this big meter stick into smaller parts. And you can see it is actually divided into smaller parts. Is that right? Now, a meter stick is divided into 100 centimeters, and each centimeter is divided into millimeters, and so on. Let's look at some of these divisions. So how do we use units in order to measure large distances and small distances? Now, look at the terms that we will use. We will start with the meter. And now, I'm going to take you to the left. To the left of the meter, we have units that are used in measuring small distances. And I'm going to say meter is 1 unit. Is that right? 1 unit. And I wrote it 10 to the power of 0. And 1/10 of a meter is called a decimeter. Look at this, 10 to the power of -1. 1/10 of a meter. 1/100 of a meter is called a centimeter. So how many centimeters are there in a meter? A centimeter is 100th of a meter. That means there are 100 centimeters in a meter. How about millimeter? A millimeter is 1,000th of a meter, 10 to the power of -3. A micrometer is a millionth of a meter, 10 to the power of -6. A nanometer is a billionth of a meter, 10 to the power of -9. And how about picometer? Is a trillionth of a meter, 10 to the power of -12. Well, I will show you how to write these. Centimeter is lowercase cm, millimeter is lowercase mm, micrometer is the Greek letter mu. I will show it to you as we go on. Mu m, nanometer is nm, and so on. All right, so these are the units for measuring very small distances. Let's now go for large distances. What does deca mean? What's a decade? A decade is 10 years. A decameter is 10 meter, 10 to the power of 1. A hectometer is 100 meter. A kilometer is 1,000 meter, 10 to the power of 3. A megameter is 1,000,000 meter, 10 to the power of 6. A gigameter is, what do you think? Is 10 to the power of 9 meters, which is 1,000,000,000 meter. And finally, a terameter is 1,000,000,000,000 meters. So we have now units that are used for measuring very small distances and very large distances. Similar measures are used for measuring small and big masses. You know, in measuring mass, what is the unit for measuring mass? It's a kilogram. So in place of the meter, we will write a gram. And gram is a G. Gram, decigram, centigram, milligram, microgram, and so on. Decagram, hectogram, kilogram, that's our unit, megagram, and so on. So we can use the same quantities, same terms for measuring mass as well. Now, how about measuring area, volume, speed, density, and so on? These are examples of physical quantities that have units that are derived from the fundamental units. So, in order to obtain the units of area, volume, speed, density, and so on, we combine the units of the fundamental quantities. Therefore, the units of such quantities are called derived units. Derived units. They are derived from the fundamental. For example, the area, the unit of area. Now, what does area? How do we calculate the area of a piece of paper? Length multiplied by length. Length is measured in meter, width is measured in meter, therefore area is measured in meter multiplied by meter, which is a square meter. Similarly, the unit of volume is a cubic meter, meter cube. What is the definition of speed? Speed is the rate at which distance is being covered. Is that right? That is distance divided by time. So what is the unit of speed? Distance is measured in meter. Distance is in length. Time is measured in second. So the unit of speed is meter per second. Meter divided by second. And look at the way we write it. The standard way to write this is meter times second to the power of -1. So we will not write units like this. We will write units like this. Meter second to the power of -1. Density. Does anybody know how density of an object is defined? Density is mass contained in unit volume. And you can measure density by dividing mass by volume. Mass divided by volume is density. Well, what is the unit of density? The unit of mass is the kilogram. Unit of volume is the meter cube. So, unit of density is kilogram per meter cube. And can you tell me how do we write it in the standard form? Well, we write it in the standard form as kilogram times meter to the power of -3. Now, this is the standard way we will write all units. Okay? Now, it is important that you learn to convert units all to the SI system before you are able to solve problems. Well, in physics, we always solve problems. And we will use units in solving problems. And if I give you units other than meter, kilogram, second, you need to convert all of them to meter, kilogram, seconds before solving the problems. So I'm going to put down these conversions, and I want you to be familiar with it. 1 meter contains 1000 millimeter, and therefore 1 millimeter is 1,000th of a meter. 1 meter contains 100 centimeter. That means 1 centimeter is 100th of a meter. 1 meter contains 1,000,000 micrometer. Look at the way we write micrometer. Therefore, a micrometer is a millionth of a meter. 1 meter squared contains 10 to the power 4 centimeter squared. Now, how does that happen? Now, if you want to find the area of a strip like this, you measure the length in meters or in centimeters. Now, what is 1 square meter? Is 1 meter multiplied by 1 meter. And 1 meter contains 100 centimeter. So 1 square meter is 100 centimeter multiplied by 100 centimeter, which is 10 to the power 4 centimeter squared. So 1 square meter contains 10 to the power 4 square centimeter. Did I say it correctly? 1 square meter contains 10 to the power 4 square centimeter. Therefore, 1 square centimeter is 10 to the power of -4 meter squared. In that case, can you tell me how many centimeter cube are there in a meter cube? Can you tell me? Because 1 meter cube is 1 meter multiplied by 1 meter multiplied by 1 meter. 1 meter multiplied 3 times. And if you write that in centimeters, it will be 100 centimeter multiplied by 100 centimeter multiplied by 100 centimeter. So 1 cubic meter contains how many centimeter cube? A million centimeter cube. 1 meter cube contains a million centimeter cube. Therefore, 1 centimeter cube is a millionth of a meter cube. Alright, let's now talk about mass. 1 kilogram contains 1,000 gram. Therefore, 1 gram is 1,000th of a kilogram. 1 kilometer is 1,000 meter. 1 hour is 3,600 seconds. All these things you know. 10 to the power of 3 is a kilo. We use lowercase k for it. 10 to the power of -3 is a milli, lowercase m. Alright, 10 to the power of 6 is a megameter. And look at the abbreviation for that, uppercase M. So how do you write megameter? Uppercase M, lowercase m, megameter. 10 to the power of -6 is called micro. 10 to the power of -9 is nano. And 10 to the power of -12 is pico, lowercase p. Alright, so I hope you are now familiar with all these measuring standards. And now, let's see how we can convert a given quantity to meter kilogram system. Convert 25 kilometer per hour to meter per second. Now, very often you will be required to do this. If I give you the speed in kilometer per hour, you need to convert that to meter per second. Alright, now watch how I do that. I'm going to first of all write 25 kilometer per hour like this. 25 kilometer divided by 1 hour. And in the next step, you need to say 25 kilometer. Now, each kilometer contains how many meter? 1,000 meter. So write this as 25 times 10 to the power of 3 meter. You see, 25 kilometer is 25 times 10 to the power of 3 meter. And 1 hour is how many seconds? 3,600 seconds. You can see the unit is now meter per second. Alright, simplify this, what do you get? That will be 25 divided by 3.6 meter per second. Now, you will ask me, why did I write it like this? Well, I wrote it like this for one reason. In order to convert kilometer per hour to meter per second, what all you need to do is divide that number by 3.6, isn't it? Kilometer per hour can be converted to meter per second by simply dividing by 3.6. So 25 kilometer per hour is 25 divided by 3.6 meter per second, and that is 6.94 meter per second. Alright, we will be doing this very often as we go on. So when I ask you to convert kilometer per hour to meter per second, what all you need to do is divide by 3.6. Alright, let's do another conversion. Convert 3.5 gram per centimeter cube to kilogram per meter cube. Okay, we will do the same thing. Write it like this. 3.5 gram per centimeter cube is the same as 3.5 gram divided by 1 centimeter cube. And in the next step, you got to convert the gram to kilogram. Now, how do you convert gram to kilogram? A gram is 1,000th of a kilogram, 10 to the power of -3 of a kilogram. So 3.5 gram is 3.5 times 10 to the -3 kilogram. And centimeter cube has to become meter cube. What part of a meter cube is a centimeter cube? Well, we talked about it. 1 meter cube contains 10 to the power 6 centimeter cube. So 1 centimeter cube will be a millionth of a meter cube. 10 to the power of -6 of a meter cube. So a centimeter cube is 10 to the power of -6 of a meter cube. And when you simplify this, what do you get? That will be 3.5 times 10 to the 3 kilogram per meter cube. So you must be well versed in the art of converting units like this. Okay, let's do a simple problem. The radius of the Earth is 6,700 kilometers. Find the volume of the Earth and express it in cubic meter. Well, the Earth is a sphere. Now, how many of you know the formula for the volume of a sphere? Well, you need to know that. You've all done college algebra, pre-calculus, calculus 1, and some of you calculus 2, right? The volume of a sphere is given by V equal to 4/3 pi r cubed. So there's nothing more in this problem except use that formula. And r, the radius, is given in kilometer. We need the answer in cubic meter. So you need to convert kilometer to meter cube. So here, the radius r is 6,700 kilometer. That is 6,700 times 1,000 meter, 10 to the power of 3 meter. And that is 6.7 times 10 to the 6 meter. So use this value over here. V equal to 4/3 pi r is 6.6 times 10 to the 6. Well, it should be 6.7. You make that correction. And that will be approximately 1.26 times 10 to the 21 cubic meter is the volume of the earth. All right. Let's now look at the concept of dimensions. All physical quantities can be expressed using their dimensions. What is the meaning of a dimension? Dimension of a physical quantity indicates the nature of the quantity measured. Now, we will represent the dimension of length by the uppercase L. So when the quantity measured is length or distance, diameter, radius, you see that? All of them are lengths. And what is the dimension of such quantities? Uppercase L. The dimension of mass we will represent by uppercase M. And the dimension of time we will represent by uppercase T. So, the three important dimensions of the fundamental quantities. What are the fundamental quantities? Length, mass, and time. The dimensions of the fundamental quantities are uppercase L, uppercase M, uppercase T. Now, let's use this to solve a simple problem. We got the equation x equal to 1/2 at squared. X is the distance that has the dimension L, is that right? T is the time that has the dimension uppercase T. This T should have been that lowercase t. This is time. And the dimension of time is uppercase T. What is the dimension of A? So, in order to find the dimension of A, what all we need to do is use the dimensions of X and T and then solve for A. That's all we need to do. We replace each quantity by its dimension in that equation. So look at this. X is replaced by L, the dimension of that quantity. And T squared, time squared, is replaced by the dimension of that quantity, uppercase T squared. A, we don't know the dimension. Now tell me, what is the dimension of the number 1/2? A mere number has no dimension. So this is dimensionless. That means you can drop it from that equation altogether for this problem. So solving for A, let's solve for A first. Solving for A, can you do that? A will be 2L divided by T squared. And we can drop 2 from here. Why? Because 2 has no dimension. And therefore, what are the dimensions of A? The dimension of A, therefore, is L divided by T squared. And this is not the standard way to write it. You see, dimensions must be written in the standard way like you write the units. So how do we write this in the standard way? It will be written LT to the power of -2. The dimensions of this quantity A is LT to the power of -2. And you will see a little later that this A stands for acceleration. The dimensions of acceleration is LT to the power of -2. In that case, let me see if anyone can do this for me. What are the dimensions of speed? Can you tell me? Send me a note if you want. All right, what are the dimensions of speed? Okay, let's go and look at another problem. Some of the physical quantities we use in this course and their dimensions in terms of L, M and T, the dimensions of length, mass and time are, I'm going to give it to you in here. Area, the symbol is A. What is the dimension of area? Area is length multiplied by length. The dimension of area is L squared. Volume is V. The dimension is L cube. Length multiplied by length multiplied by length. So the dimension of volume is L cube. Speed. Well, I asked you, is that right? I'm sure most of you got it. We represent speed by V. Its dimension is Lt to the power of -1. Distance divided by time. So the dimensions of speed is Lt to the power of -1. Acceleration, we just did it, Lt to the power of -2. Density, we generally represent density by the Greek letter rho. You've got to practice that, rho. And what are the dimensions of density? Density is mass divided by volume. The dimension of density is ml to the power of -3. Okay. Let's use dimensions to solve a problem. The period of a simple pendulum is known to depend on length and acceleration due to gravity. What is a simple pendulum? Well, this is a simple pendulum, if you can see this. Now, I have a metal ball suspended by a string. I can set it into oscillation. The period means the time taken for one oscillation. Don't worry about it. We will talk about it in Physics 2. We will talk more about it. But in this problem, what does it say? The period of a pendulum is known to depend on its length and acceleration due to gravity. Well, what are you supposed to do? All right. The period of oscillation of a simple pendulum is known to depend on its length and acceleration due to gravity. Use dimensions of these quantities involved to obtain an equation for the period of a pendulum of length L. Now, this information is enough for us to obtain a mathematical equation for the period of a pendulum. Now, what are the quantities on which the period depend? We are told that the period of a pendulum depends on its length and acceleration caused by gravity. So, we will start by assuming that the period t is proportional to a to the power of y. What does a stand for? The acceleration caused by gravity. And also proportional to L to the power of x. What does L stand for? The length of the pendulum. So, we start by assuming that let the period of a pendulum be proportional to L to the power of x and a to the power of y. Okay, can you write that statement using a mathematical notation? Well, let me see if I can write that for you. We will write it like this. Period t is proportional to L to the power of x, a to the power of y. Now, this is the sign we use for proportionality. And in this course, and in any other science course, when you have a proportional sign, it can be replaced by an equal sign by adding a constant. So, if t is proportional to L to the power of x, a to the power of y, I can write it as t equal to k times L to the power of x, a to the power of y. Alright, we will use this concept very often in this course. So we will start it like this. Now what you now need to do is replace each quantity by the dimensions. Now on the left side, t, the period, is the time. What is the dimension of the period t? It is t itself, uppercase t. So we don't need to do anything there. And on the right side, tell me, what is the dimension of a constant? A constant doesn't have a dimension. So we will have nothing for k. This is length L. What is the dimension of length? Well, that is L itself. We don't need to do any change there. What are the dimensions of A, the acceleration? We just did it. Is L times t to the power of -2. So, period t, the dimension is t. K, let's keep k for the time being. It has no dimension. The dimension of length is L, so L to the power of x. We replace a by its dimension. The dimension of a is Lt to the power of -2, and we raise that whole quantity to the power y. And now, use the power rule. L times t to the power of -2 all to the power of y is L to the power of y times t to the power of -2y. Okay? And in the next step, we're going to write this as, now, I did some manipulation here. You know that any quantity raised to the power of 0 is 1. So, since there is no term on the left side using L, I wrote this quantity t as L to the power of 0, t to the power of 1. Did you understand that? Well, I don't need to write L to the power of 0. L to the power of 0 is simply 1. I can as well write it as z to the power of 0, because anything to the power of 0 is 1. Now, why did I do that? Because I see an L on the right side, so on the left I introduced an L. L to the power of 0. T to the power of 1 equal to k, look at this, L to the power of x times L to the power of y is L to the power of x plus y. Okay, what do you do next? We have an equation with a left side and a right side. And everything about the left side must be equal to the right side. Is that right? That's the meaning of an equation. So, if there is an L on the left side, the exponent of that L must be equal to the exponent of L on the right side. So, what we are going to do, equate the exponents of the same base on either side. What does that mean? It means 0 is the same as x plus y. So, and 1 is the same as negative 2y. The exponent of L on the left side must be equal to the exponent of L on the right side. I'm sure you agree with me there. The exponent of t on the left side must be equal to the exponent of t on the right side. So I start by saying 1 equal to negative 2y, and that gives me the value of y. Y equal to negative 1/2. Now, also equating the powers of L, we have x plus y equal to 0. What does that mean? It means x equal to negative y, x equal to negative y, but y equal to negative 1/2. Therefore, x must be positive 1/2. See, look at the way we have been able to obtain the values of x and y. And therefore, what is the equation for the period of a pendulum? We go back to this equation, replace x by 1/2 and y by negative 1/2. So, this is the equation of the pendulum now. T, the period, equal to a constant k times L to the power of 1/2, a to the power of negative 1/2. I'm sure you know that a power 1/2 means a square root. So L to the power of 1/2 is square root of L. And what is a to the power of negative 1/2? It is 1 over a to the power of 1/2, which is 1 over square root of a. So how do you now write this in a more civilized way? That will be t equal to k times square root of L over a. And this is t, the period of the pendulum, is a constant times square root of length divided by acceleration caused by gravity. That's a beautiful equation. And you see how simply we were able to obtain it by using the method of dimensions. In physics 2, we will obtain this equation using the oscillations of a pendulum. Okay, let's now talk about significant figures. It is very important that we use numbers in their correct form. You see, every physical measurement involves a level of accuracy dictated by the instrument you use for measuring. For example, what is the accuracy of this meter rule? The smallest division that is marked on the meter rule is 1 millimeter. You cannot measure a distance less than 1 millimeter using this ruler. So the accuracy of this ruler is limited to 1 millimeter. Now, the accuracy of measurements is very often represented by using significant figures or significant digits. And you must be familiar with how to use significant digits. Measurements always involves a level of uncertainty. And we use significant figures to deal with this uncertainty. Significant figures are determined using some rules. And let's look at some of these rules. 1. Zeros at the beginning of a number are not significant. For example, 0.00257 has only 3 significant digits. What are they? 2, 5, and 7. The first 3 zeros are not significant in that measure. Rule number 2. zeros within a number are significant. For example, 20.06. How many significant digits are there? It has 4 significant digits. That means 1, 2, 3, 4. Both these zeros are significant. Rule number 3. Zeros at the end of a number after the decimal point are significant. For example, 5.0. Now, a number 5.0 indicates that you are making measurement correct to 1 decimal place. That is a level of accuracy dictated by this. That 0 is significant. So, zeros after the decimal at the end of a number are significant. Now, 5.0 times 10 to the power of 2 has 2 significant figures, while 5.00 times 10 to the 2 has how many significant figures? Has 3 significant figures. That means in this measure, we expect an accuracy of 1/10. In a measure like this, we expect an accuracy of 100. So this is a much more accurate measure than this. Okay. When you report a final result, how many significant digits should there be? The final result of an operation should contain the same number of significant digits as the quantity with the least number of significant figures that was used in a calculation. Now, let's illustrate that with an example. The base of a triangle is 7.2 centimeter and its altitude is 4.35 centimeter. Find its area. Alright, what is the area of a triangle? If you notice, 7.2 has 2 significant figures, 4.35 has 3 significant figures. Tell me, using this rule, how many significant figures should there be in the answer? What does the rule say? The final result of an operation should contain the same number of significant figures as the quantity with the least number of significant figures that were used in the calculation. So we are using 2 numbers for our calculation. One has 2 significant figures, the other has 3 significant figures. Therefore, our answer must have 2 significant figures. Alright? If B is the base and H is the height of a triangle, then the area of the triangle is given by A equal to 1/2 of BH. Well, we know the base, we know the height, so that will be 1/2, 7.2 centimeter times 4.35 centimeter. You should write those units there, which is 16 centimeters square. You can see I wrote the answer using 2 significant digits, and that is what I expect you to do also. Okay, now this has been a summary of measurement, units, significant figures, dimensions, and so on. If you take a lab with me, I will elaborate on this in the first lab. In fact, the first lab is the use of units and conversions, so that you get to know this in a little more detail. Alright? You need to go through that and make sure you understand these concepts very well. I'm going to stop this here. I'm going to continue with lesson 1.1 as a second part. I'm going to call it lesson 1.1b. I will be doing that throughout this course. In my lectures, I will divide each lesson into smaller units so that you don't have to watch a lesson for a long period of time. And in our next part, we will be starting our discussion on moving objects. And all these concepts we discussed, we will be using in there. All right, I will see you for that lesson a little later.